Good evening, everyone. Today I will be teaching a centrifugal separation process. Um, Before starting, I will wait a few minutes more for people to join for the live session. Okay, so we can start now. So today we are going to start centrifugal separation process. So centrifugal separation is a more accelerated form where we separate solids or uh, solid from liquid strings, or you can also say liquid and liquid strings based upon the density and other differences that we will discuss. So this centrifugal separation process is very important in terms of the industry, because there the process needs to be very fast for separation, and somewhere there are gravitational process. Sometimes it takes a lot of time when the specific properties of the um, different materials and similar, then this gravitational process or gravitational sedimentation process may take several days or several hours. So to make faster the process, we go for the centrifugal force application. So this centrifugal separation process can be regarded as the extension of gravity separation process, where the settling rate of the particles in centrifugal separations are improved under the influence of the centrifugal force. So this centrifugation process is a mechanical process that uses centrifugal force to separate particles from a solution based upon their size difference or shape difference, density difference, medium viscosity, and also difference in the rotor speed. So here the denser components of the mixture, denser or the heavier component of the mixture, they migrate away from the centrifuge axis of rotation, while the less denser component migrate towards the axis of rotation. So this centrifugal field is created by introducing a fluid with a very high tangential velocity. So always in the centrifuge, tangentially feed input is practiced generally, and it is being carried out in a cylindrical or conical vessel. As you can see in hydrocyclone, or in case of the any kind of cyclone separator, those are basically cylindrical or conical vessel in shape. So if the fluid is rotating, then in the vertical direction, gravity becomes predominant. And in the horizontal axis, centrifugal force becomes important. And you know that gravitational force is denoted as G, where the horizontal force or centrifugal force is denoted by r omega square, right? So when it is a very larger and heavier particle, as they are thrown away from the axis of rotation, thus they will be collected near the wall of the vessel, where the smaller and rotating bowl is uh, okay, where the smaller particles will be collected inside the rotating bowl near the axis of the rotation. And you can see that rapidly there will be acceleration of the lighter particle, which will be taken towards the axis of the vessel. So in a centrifuge, the fluid is introduced into a rotating bowl and they are rapidly accelerated. This RPM of the centrifuge vessel is generally very high because of the frictional drag within the fluid that ensures that there is a very little rotational slip or frictional loss between the moving fluid layers within the bowl, and all fluid will tend to rotate at a constant angular velocity. So these are some basic knowledge about centrifuge vessel or centrifuge operation. So this is here typically we do mini centrifuge in research laboratory. Here these are some centrifuge tube, generally looks like this. This is the cap, and the centrifuge tube also look like this. More or less it looks like this. So these tubes are inserted into the designated places when it is, and most of the time this centrifuge tube, if you are putting in number 1, so it should be counterbalanced. So that's why the centrifuge operation works. And what happens that this is, you close this lid you close this and switch on this and it will rotate. So when it rotates it feels like this. You can see this is the axis of rotation, this one, and this is the orbit. And here suppose this is your centrifuge tube where there is working one centripetal force, and this is the velocity of rotation, right? So when this kind of operation we are doing before centrifugation, the particles are well dispersed, but after centrifugation all the particles are settled down. So this is why we use centrifuges in a larger application each and every day in the research purpose in the laboratory. This is kind of a smaller version, but in industry also there are certain big type of hydrocyclone are there where you can get many applications. So some of the application that I have pointed out, that is separation of the blood cells or protein or DNA. We use this kind of separation centrifuge instrument. Then ultracentrifugation of macromolecules and viruses. Then cell harvesting or purification, cream separation from the milk, juice clarification or its purification, oil refining and purification, sludge thickening and then dewatering in the wastewater treatment, extraction of fine particles from previous very precious metals from loose ores and tails, then removal of the fine particles in spent fuel reprocessing. And also there will be solid drying and crystallization. So these are some operations that we look. So we are moving towards the um, main part of this today's session. That is, when we are using the centrifuge, what will be the shape of the surface, liquid surface, under the centrifugal force. So here you can see that this one this one is the surface, liquid surface. Okay, so here is your main, suppose one particle is there. So when it is rotating in such a orbit, this is the complete orbit, suppose. So the radius of the centrifuge bowl is r, and the axis is in the z direction. So this is the particle, it is going following this rotation. So here in the axial direction, there will be force, that is r omega square, that is your centrifugal force, which is the radial component of the force acting on the particle. It is not the particle, it is a point A. So you can say at point A, the centrifugal force is r omega square. It acts as radial component of force. Similarly, at point A, the gravitational force is G, which acts in, because the axis is in the z direction, so it acts as a axial component of force. So here, when you do these two forces you have, so you have one resultant force. So R is the resultant force. So when you have this at point A, what is the slope of this? So you put a slope. So at point A, the slope becomes dz naught equals to the radial component, that is r omega square, divided by the axial component, that is g. So if you do the integration, so you will get z naught equals to omega square r square by 2g plus some constant. So we need to solve this equation to understand the value of the constant. So one boundary conditions you can assume. So consider you are having at r naught equals to 0. That means at the center of the orbit, the position of the free surface is denoted as ZA. So these equations become, this equation becomes Z naught minus ZA equals to omega square r naught square by 2g. So this is one we got when we solve the okay. So next what we have, that we have discussed that we got a new uh, that is ZA, which is noted as position of free liquid surface at axis of rotation. So this Z is positive when the bottom of the bowl is completely covered by liquid. But this ZA is negative when the free liquid surface becomes paraboloid. It means that the free surface would cut the axis of rotation below the bottom and the central portion of the bowl will be always dry. So now a condition appears when the centrifugation is happening at a very high speed. When centrifugation is occurring at a very high speed, Then the conditions appear when this term r square omega square, this term is very greater than g. And this always when you deal with industrial um, applications, always they operate centrifugation at a very high speed. So this it means that r square by 2g it's also very greater than 1, right? Okay, I will not write in the same thing, maybe it is confusing. So in this position the free surface becomes nearly vertical. In this situation the free surface becomes nearly vertical instead of getting parabolite, and for that ZA becomes very negative. So this is when we got a clear idea about how the free surface of the liquid acts under centrifugal force. So in the next topic we are going to discuss that how the centrifugal pressure acts in the centrifuge. So this is one centrifuge. So this is the free surface of the liquid. This one is the axis of rotation. This one is the free surface of liquid. This one is the breadth of liquid, the total centrifuge. This one is the uh, free surface, and R2 is the radius of the centrifuge bowl. While we have taken a elemental uh, unit or elemental form of liquid, a thin film of thickness dr, which is located at a distance r from the axis of rotation of the centrifuge. So we are going to discuss now that what would be the case of pressure difference due to this centrifugal action. So this elemental form, which is at a distance r, also has a mass dm. So elemental liquid film, it has mass dm located at a distance r from the axis of rotation of the centrifuge bowl. So what would be the centrifuge force? Centrifugal force for that elemental liquid, that is dF, r omega square dm, where this dm, mass of the liquid in that film, dm equals to 2 pi rb into dr into density. So this equation 1 becomes df equals to 2 pi r square omega square b rho dr. Now we know the basic definition that the pressure over the liquid element, that is centrifugal force by area. So this dp equals to df by 2 pi rb. So when you just write down this equation, omega square b rho dr by 2 pi rb, it becomes omega square rho r dr. Okay, so we want to know what is the pressure drop over the entire rim. That is P2 minus P1 equals to integration of R1 R2 omega square rho R dr. So for that we are getting P2 minus P1 equals to rho omega square by 2 R2 square by R minus R1 square. So this is one the pressure drop we generally get when we are operating the centrifugal separation between two liquids in such an arrangement. So next we are going to discuss about the separation of immiscible liquids. So when we go with the gravitational separation process, there we face lot of issues when the densities of the two liquids are very similar, right? So, and there are also immiscible liquids we separate through the centrifugal action, which is very fast and very effective. So here in this picture you can see this phase one feed is introduced. Liquid A is heavier and liquid B is the lighter. The free liquid interface, the free liquid surface is RB, and free liquid surface of liquid A, which is RA, and the interface is Ri from the axis of rotation. So here, if the solids are also present in the liquid streams, so we can see that this can be separated in the centrifuge action, right? So here, this zone A, which is heavy liquid, uh, which is next to the inside wall of the bowl. It has the density rho A and situated at distance RA. Similarly, zone B is the lighter liquid, density rho B and situated at a distance RB. And the interface of two immiscible liquids is at Ri. So we also assume the frictional loss or slip is very negligible. So the pressure difference in the interface side and the side B and the pressure difference of side A will be equal if there is no frictional loss. Now we have already derived the equation. We just put for liquid B R1 is Ri square minus Rb square divided by 2, whereas omega square rho A Ri square minus Ra square divided by 2. When you solve this equation, you will get the interface I, which is also known as neutral zone. So this Ri denotes the radius of the neutral zone. This, when we solve this one, we get the equation Rb square divided by 1 minus rho B by rho A. So this one is your equation for finding out the this one is for radius of neutral zone. So you need to understand that if the pressure difference between A zone and B zone is less than 3%, then only you will get a very stable operation. Stable operation means good separation between the solids of two immiscible liquids. So generally, when we were talking about immiscible liquids, so it is kind of operations where gravitational process becomes very difficult to carry. Also, the important thing over this section, that is uh, this radius of the neutral zone, which is very important operation to look into when you are operating the centrifugal um, centrifuge using immiscible liquids. This if the radius of the this RB is getting um, increased while keeping the RA constant, then the neutral zone that will shift towards the axis of rotation, and the vice versa will occur. Similarly, when the RB is held constant and RA is increased, then the neutral zone will shift wall towards the uh, wall of the bowl. So here, thus we can vary the liquid interfaces, and we can shift the neutral zone radius accordingly. So there are a lot of centrifuge operations in a bigger centrifuge in the mineral industries, where the fine solid particles are very difficult in other means to separate from the rest of our minerals. So for that, we go for this higher effective centrifuge. Generally, these centrifuges are very shorter, because if the centrifuge is short in height, then it is more effective. So there are series of centrifuges being installed where the gas streams are passing through each of the centrifuge, and effectively fine solid particles are separated from other material. Obviously, the size of the material and the density of the material is very crucial to handle the centrifugal operation. Next, now we are going to discuss tubular centrifuge. So this tubular centrifuge, it rotates at a very high speed to reach the working speed suitable in industry, and it is the speed remains 15,000 rpm, and the separation factor is over 15,700. So in this tubular centrifuge, it is very effective to separate the very fine or tiny solid particles in the liquid, and they clarify the liquids by removing those solid impurities. So here you can see that the feeding is being done at the bottom of the centrifuge, and it goes up where the light liquid will go from the inside chamber or very close to the axis of rotation, because this is the uh, lighter or light density liquid, so it will be collected in this way, where the heavier liquid or more denser, that will be collected in the other form, and all the solid phases will be collected away, very far away from the axis of rotation, inside the bowl at the um base of the bowl. So this tubular centrifuge is mainly used for liquid solid and liquid liquid two phase separation, and most of the other cases it also works with liquid liquid and solid, that is three phase separation process. The separable particles can reach up to zero point 0.1 micron and very low solid contents. Here the mixed suspension is continuously fed from the bottom, and the suspensions are layered under the action of centrifugal force. So this centrifuge is also rotating in such way, and there is effective separation between the density difference to liquid and the solid phase. So this is also three phase separation. The two liquids in the suspension have their difference in their densities, and they are incompatible with each other. The liquid phase spirally rises gradually from bottom to top to the upper part of the rotor, that is this part. And the liquid phase with a smaller density, or the liquid that is lighter, they are discharged from the light liquid outlet, and the liquid phase which is larger density will be discharged in other way. And the solid phase density which is the largest density, they will simply settle down inside the bowl far away from the axis of rotation. This high speed tubular centrifuge separator is very suitable for clarifying the separation of the materials, which has very low solid content, that is less than 2%, while the other centrifugal equipment is recommended for the material which has very high solid content, like greater than 5%, as a pretreatment process. So, this in this lecture, we have discussed about most important centrifuge. We are now going to discuss the next part, that is the disc centrifuge. So this disc centrifuge, it has the bowl has the flat bottom and a conical top. The feed enters from the above through a stationary pipe which is set into the neck of the bowl. Now the two liquid layers which are formed in a tubular centrifuge, they flow over adjustable dams into separate discharge. Here the feed enters at the bottom and flows into the channel upward the past disc. Heavier liquid is thrown outwards and displacing the light liquid towards the center of the bowl. While being thrown outward, this is heavy liquid very soon strikes underside of a disc and flows beneath it to a periphery of bowl without, without encountering any light liquid. Similarly, the light liquid flows inward and upward over upper surface of the disc. So since discs are come closely spaced and distance a drop of either liquid must travel to escape from other phase is short, much shorter than in comparatively thick liquid layers in a tubular centrifuge. In addition to that, in this machine there is considerable shearing at liquid-liquid interface. Then the disc centrifuges are particularly valuable, but the purpose of centrifuging is not complete separation only, but concentration of the one fluid phase is very important. Now we are going to discuss the centrifugal sedimentation process. So here the feed is introduced and from the bottom. This R1 is the liquid free surface, RA is the initial position of the particle, RB is the final position of the particle, and R2 is the bowl actual radius, and this one is the axis of rotation. So particle where it settle down in the trajectory, it was initially at RA and it will settle down at RB. If the condition persists that RB is less than R2, then particle they leave the bowl with liquid stream. But if Rb equals to R2, then particle they deposit on the bowl wall and removed successfully from the liquid stream. So now we are assuming this is following the Stokes law. We get the terminal settling velocity of the particle r omega square rho particle of rho liquid dp square by 18 mu, where ut we can also write it as dr by dt. So when we do the integration of dt equals to integration of 18 mu by omega square rho p minus rho dp square dr by r, 0 to terminal and this residence time, where the particle will move from location Ra to Rb. So what will be the residence time for the particle? That is 18 mu omega square rho p minus rho dp square ln of Rb by Ra. So this one is the your equation. So you want to now estimate what is the volume of liquid in the bowl. That is V equals to pi b R2 square minus R1 square. From there, you can easily calculate what is the volumetric flow rate. The volumetric flow rate becomes Q equals to V by T, that is dp square pi b R2 square by 18 mu omega square rho p minus rho by ln of Rb by Ra. So here we want to define the cut point diameter. The cut point diameter, that the die of the particle which just reaches the halfway between this R1 and R2. It reaches the halfway. So for volumetric flow rate, corresponding to cut diameter, that will be Rb equals to R2 and Ra equals to R1 plus R2 by 2. So considering this, the cut point volumetric flow rate becomes omega square pi b rho p minus rho dpc 18 mu R2 square R1 square by ln of 2R2 R1 plus R2. Okay, so in this condition of volumetric flow rate, if dp is greater than dpc, then this is eliminated by centrifuge. But if dp is less than dpc, then they will remain in liquid. Also, if the thickness of the liquid layer are very small in comparison to the bowl, it may appear that R1 equals to nearly equals to R2. Then the particle settling velocity will get constant. So now, if the situation occurs that R1 nearly equals to R2, then particle settling velocity becomes constant. That is ut equals to R2 omega square not c, this is dp square by 18 mu. And suppose this small thickness of the liquid layer is S and particle of cut diameter, they travels a distance S by 2. So this velocity becomes S by 2, and this can be denoted volume by volumetric flow rate. So this volumetric flow rate at cut diameter will be 2V ut by S, which is nothing but 2V dp square rho p minus rho R2 omega square 18 mu S. Now taking in the centrifuge operation, taking all the averages of this R2, this equation can be written as QC equals to 2V RE square omega square by G into S into dp square rho p minus rho G by 18 mu. So from this we can write QC equals to sigma value into UG. So this sigma value is the value cross-sectional area of a gravity settling tank which has the same separation capacity as centrifuge, and UG is the terminal settling velocity under gravitational force. So now what we are going to discuss about the hydrocyclone part. So hydrocyclone, that we are already discussed that how important this is for separating the very fine particles from the gas stream. So separation is very effective when it is in the centrifugal force and generating introducing the fluid at a very high tangential velocity into the separator, and it causes the fluid to rotate inside the cone. You can see these are the very fine solids that are being collected at the bottom. No, the heavier particles will be collected at the bottom. The mechanically it is not mechanically rotating, so it needs some pump to uh, inject into very high tangential velocity. The flow pattern within the hydrocyclone is um, very complex, and there are velocities, three type of. The tangential velocity will give rise to the particle to the centrifugal force and critical to operation of the hydrocyclone. Tangential velocities of the liquid and solids may up to 20 meter per second, and the radial velocity is much lower than the tangential velocity. However, the within the device, there is net flow of the liquid towards the center, you can see, and the net flow of the solids away from it. Hence, it is important to distinguish between the radial directional flow and the solid flow. The third velocity is the axial direction. This velocity has to be considered carefully because the hydrocyclone has two outlets continuously splitting the feed into different streams. The overflow contains a suspension that is more diluted than the feed and has a finer particle size distribution. The overflow are fines. So by contrast, where the underflow is more concentrated and this has coarser size distribution. So this bigger one is the primary vortex. It goes down and then it goes this way. So this one is secondary vortex. Thus the hydrocyclone acts as both a thickener and as classifier. The axial velocity must take material to the two outlets and the suspension near to the wall of the hydrocyclone flows axially to the underflow. So the material near to the center of the hydrocyclone flows axially to the overflow. Hence there is axial flow downwards and upward within the hydrocyclone also. So in a hydrocyclone, the pressure drop varies with the feed rate raised to a power between 2 to 3.3. For very diluted feeds, the cut diameter varies with 1.5 power to the power cyclone diameter. So the even this pressure drop is very so for a given pressure drop, a smaller diameter gives better separation than the larger one. So hydrocyclones are usually kept as a smaller in size. Next, we are going to do some numericals. So it is given that a centrifuge clarification system is used to eliminate the settled solid from the liquor resulting after the fermentation process. The solids have a density of 2300 kg per meter cube and they are suspended in water at a very low concentration. This clarification completed by a large centrifuge having sigma value 2000 meters square and a capacity of this is the volumetric flow rate. So what will be the effective cut size in microns where other densities are mentioned? So right now, what are the given data? That is particle density is 23, sigma value 2000, flow rate at cut diameter condition that is 1.6, density of the fluid that is water, and viscosity of the fluid that is of water. So you have to calculate what is the cut diameter. We know that the equation tells QC equals to summation into 2 UG. What is UG? dP square rho p minus rho by 18 mu into sigma value. So when you solve this equation, you will get dP square value as 18 mu QC by 2G rho p minus rho into sigma. So when you solve this, you will get dPc value as 5.646 into 10 to the power minus 14, from where you will get dPc value as, after converting, this is in meter, after converting into micron, you will get around 0.24 micron. So this one is your answer. This is very simple forward. You have to apply the condition for cut diameter. Now we will move to the next question, that is the same type, where a centrifugal clarification system is used to eliminate the settling solids from the liquor resulting after fermentation. So the solids have a density and they are suspended in water at a very low concentration. The sigma value is given and the volumetric flow rate is given. If a large centrifuge is used with the sigma value higher, what will be the capacity or volumetric flow rate for that case? So we will use the same equation, but before that you have to note down what are the given data. Condition 1, that is 220 meters square. Condition 1 was, what is the QC when condition 2 sigma is meter square. So we know that QC is proportional to sigma. So QC2 by QC1 will be nothing but sigma 2 by sigma 1. Sigma 2 was this, sigma 1 was this. Then QC2 equals to it becomes 9.019 into 10 to the power minus 5 meter cube per second. Very straightforward solution. Now we will quickly go to the next question and the last question of today's session. So it is written that a liquid detergent solution having some viscosity, and it has some density as well, is to be classified of fine Na2SO4 crystal by centrifugation. So this pilot runs in a laboratory super centrifuge operating at a certain RPM at a throughput 5 lb per pounds per hour. So centrifuge bowl has um, this much long internally with R2 equals to this and R2 this. So you have to calculate the cut diameter for that. So it is also very um, straightforward that throughput is given 5 lb per hour. lb to we have to convert it into gram, that is 430 into 59 divided by 306 grams per second, and then we will just convert this to centimeter cube, that is 1 by 0.8 gram per centimeter cube. So it is coming around 0.7875 centimeter cube per second. Now all the details are given here. 19.69 centimeter, R2 2.22 centimeter, R2 minus R1 is 1.508 centimeter. Mu is given 1000. Not 1000, this is 100. Mu is given at 100 Cp, which is nothing but 1 gram per centimeter second. This omega, 2 pi n by 60, 2 pi 2300, 23,000 divided by 60 second. So you have to just calculate the QC. Has the equation this is dPc by 18 mu R1 square ln of 2R2 R1 plus R2. So this one is given as this value. By solving this, you will get dPc as centimeter. So this is also straightforward. So we have discussed about main equipments for as centrifuge separator, and we have also solved some numerical which is important regarding the throughput or regarding the cut diameter calculation. So in the next class we will learn about the flotation process which is very important for coal processing unit, very important. So we will discuss that in the next class, and the next class will be the last class for this course. So if there is any question for today's session, you can post me message, and you can message me and we will try to solve